Hi, this is Jeff Coronado at JCSC, and welcome to a session in Bridging the Gap. So, Bridging the Gap is a series of structural engineering design tutorials that we have created here at JCSC for younger engineers, whether you are currently in school, in college, and aspiring to be a design structural engineer, or you've gotten out of school within the last few years. Structural engineering can be a very challenging field to get into, as many of you may know. There will be very few opportunities for the large number of graduates that come out of school. So anything that would give you a heads up, that would give you an inroads, if you will, to bridging the gap from what you have learned in school to what you will actually need to know to be able to practice, I think would be a welcome to you and helpful to you. So with that said, let's jump into the session that we're covering here right now, which was kind of prompted on a question. So it's basically, how do you calculate the shear wall design? Notice how I'm saying design, the shear wall design gross overturning moment. And so not only are we going to calculate the gross overturning moment, which is a very theoretical process, but also how do you then adjust that overturning for design purposes? Um, so before we get into that, a little bit of housekeeping, I guess. Please, if you find this tutorial to be helpful to you, please appreciate if you give us a thumbs up at the end of the session. Any comments, by all means, will be welcome. Any questions that you might have based on this would be welcome, and we'll try to point you in the right direction. And also, if you find it helpful, please subscribe to our channel. That way, you can be notified of additional sessions when we do put them up on the channel. So with that said, let's jump into what we have here. So this is a representative type 5 shear wall panel. By type 5, we mean light framed wood construction, okay? And if some of that gets by you, by all means, let us know, because I do believe we have other tutorials, other sessions in Bridging the Gap that do cover the types of construction and what's meant by type 5, what's meant by light frame construction. So just let us know, and we'll try to point you in the right direction on which session in Bridging the Gap you would want to go to for answers on that. But this is an elevation of a shear wall panel. You can see, let me use the spotlight here. So right here are our vertical studs, right? Those are the dashed red lines that are oriented vertically. So those are our studs. These are our wood structural panels. So this is a wood structural panel. These are wood structural panels nailed, butting up into each other. Right here, you would have a representative opening. So this might be a door, as it's illustrated right now. It would be very similar if this was a wall. If this was a wall. If this was a window, then you might see some framing down here, right? And so kind of maybe some studs oriented this way. Um, and so the window will draw kind of an X to represent the opening, window through here. So whether this is a door or a window or just a wall end, let's just say the wall ended right here, kind of covers all scenarios, right? Representative scenarios of what a type 5 shear wall would look like. Okay, now let's move down to the plan view that we're going to be looking. So this looks like this is a one-story residence. So you can see the roof edge. Let me use again the spotlight. The roof edge comes along here. So all of this is the roof edge right across here. It looks like we have repetitive framing. Specifically, it looks like these are trusses, but we have repetitive framing that goes in this direction. I believe here north is up, and I'll just show that over here. So we'll call that north. So the framing is going north-south in this roof. Let me clear the screen. What else do we have? So in particular, we're going to look at what we would call the shear wall line across the north perimeter of the residence. All right, so that's our shear wall line. All right, now that we've identified the shear wall line, let's actually look at the piers that we have within that shear wall line. So the piers of the shear wall would be this line segment, this line segment, see, this line segment, and this line, oops, and this line segment. Okay, let me show you in yellow. In yellow, these are headers, meaning these are wall openings, whether it's a door or a window, not sure. But in the segmented approach, we're going to ignore those openings for our shear wall calculations. And then you might ask, well, there's also a small pier here at the end. Why are we ignoring that? Let you think about that one for a second. Okay, if the answer was, if you came up with the fact that that's too short, you'd be right. That is too short. We would need to ignore that. Why do we know that's too short? That's covered in another bridging the gap. Okay, so aspect ratios of type 5 shear walls. Let me know and drop us a note there in the questions afterwards, and we'll try to cover that for you, try to point you in the right direction as far as which bridging the gap session you'd want to look at. Okay, so with that in mind, the next thing that we need to do, let me clear the screen here. Next thing that we need to do is identify the critical end of the critical pier. So again, I believe this is covered in another Bridging the Gap session, because that is somewhat of an art. And by that, I mean there's judgment involved. So what we want to do is a couple things. If we want to figure out which one of the piers along the line has the most overturning, is going to have the greatest uplift, we are probably going to focus on shorter piers rather than longer piers. So in other words, this pier here being a longer pier is probably not going to be the pier that's going to generate the most overturning. Then we also, so now we want to look on shorter piers and shorter piers that have the least amount of weight on it, because weight resists uplift, right? So the more weight on that pier, the more chance that it's not going to have critical uplift. Our most critical situations that we need to be aware of is where we have shorter piers with lighter loading. So in this situation, if I ignore the one that's now X'd out, let me go on to red here. Would we want to consider this pier or this pier? I would say these two piers are pretty equal, similar in length, similar in loading on it in terms of the trusses. Remember that we said the trusses are framing into, so let me use blue here, the trusses are framing into these walls, right? So there's a lot of load coming into these walls. So really, I can probably pick any one of these ends as maybe not this one, because this one, let me undo that, because this one is probably slightly longer. This one is slightly longer than this one. So the two that we're highlighting right now in magenta might be the ones that we would look at, or possibly this one over here, this end. I would not look at this end over here, because that one, let me show you in green, has all of this exterior wall that comes in and frames into that end. And that's going to help you generating resisting moment. So this is not the end that I would look at. So in reality, probably the end that I would end up looking at here to determine the design gross overturning would be this end here for this pier. And again, that's somewhat of a judgment call. That's the thinking that I would use, that I would go through in just looking at this. Obviously, once you do this a few times, this is something that's you're going to be able to make this determination within a second after looking at this line to see which one is going to be your governing gross design overturning moment. But that's kind of the sequence of thinking that I would go through to make that determination. Okay, so the next thing now that we want to cover is the unit lateral demand. All right, so now we're over here. We're covering the unit lateral demand. Again, up here is our plan view. So we have a one-story structure. We've covered that. We are doing with the process that we are following, the procedure we're following is the ASD procedure. So this is not LRFD. This is ASD, and part of the reason why we're doing ASD is because that's still, depending on what region you operate in, but what you're going to find is that I think still in most regions, ASD is still the method to design type 5 construction, even though, you know, in academia, certainly the push is for LRFD, and that might happen someday. Someday we may make that transition. But in general, in practice, what you're going to find is that type 5 construction is still designed in ASD. So we've got what we're calling W, and in this case, we're using the subscript of EQ because this was an earthquake generated force in this particular example. Keeping in mind, doesn't look too good. Let me see if I can undo that. So whether you are in a region which is more prone to earthquakes or in a region that's more prone to high wind forces, either way, this is the procedure that you would follow. It would be very similar for either one. So in this case, we're using earthquake as an example. So we come up with our unit earthquake load of 5 pounds per square foot. So that's what we've got here. Okay, so that's a representative unit load of 5 pounds per square foot of seismic load. How to determine that 5 pounds per square foot, covered in another Bridging the Gap. If you need help if you need help finding that session of Bridging the Gap, let us know. Drop us a note at the end, and we'll try to find the title of that one for you and point you in that direction. But so our starting point is W earthquake is 5 pounds per square foot for this example. Okay, so the first thing that we want to determine here is what is the lateral force, which is what we are calling the earthquake. Okay, what is the lateral force on the wall? So, and in particular, our wall pier. So we are looking for the force that is pushing from left to right on this end of the wall, right? That's what's going to generate the critical amount of that is the governing tension, the highest tension that we're going to get, uplift tension that we're going to get on this end, on this shear wall pier. along this line, right? So we remember we evaluated this wall line, we looked at the different wall piers, and we determined that out of all of the ends, out of each one of the two ends of each one of these piers, this one was the governing one. This one is the one that's going to be the most critical in terms of uplift due to gross overturning. So that's the one that we're going to perform the calculation for. So with that, we are now looking at this expression. So what we've got is that this earthquake force V is equal to W earthquake, which we've already kind of covered. That gets multiplied by the width between the walls. So the width, by that what we mean is the distance between, let me use another color here, use blue, the distance between the wall lines. So remember, this is a wall line here, and we can't see it in this image, but let's just say the next wall line is, I don't know, down here, let's say. All right, so what we're looking at is this dimension. So it's the distance between the wall lines, between the shear wall lines. Okay, so that's B walls, so that we divide by 2. The L wall gross is this dimension. Let me use blue again. So we're multiplying, yes. Well, L wall gross, we're not quite multiplying, but L wall gross refers to the gross, the overall length of the wall line, which is in essence the distance represented by the blue line here. That includes any windows or door openings that occur within that wall, that occur within that wall. That's what we refer to as the L wall gross. And then notice how we are also adding what we are calling O sub VER. So that refers to the overhangs. The overhangs, we need to add, I'm using magenta here, we need to add then this small distance and this small distance, because that generates seismic force as well. Again, this is kind of covered in another session, and bridging the gap is determining these forces. So I know that I'm going over it pretty quickly in this, because here we're trying to cover the design overturning. Then this term, notice how this term here gets divided by this factor of L effective total. So the L effective total refers to our pier. That's the effective length of our, I'm sorry, the L effective total that refers to the lengths of the piers in the line. So let me see. Let me see if I can erase this, and let me go ahead and erase that. Okay, so the L effective total would mean the length, this length, plus this length, plus this length. You know what, I'm going to have to erase the arrow too, because I can't see otherwise. So let me, oh, is this, let me get rid of this as well. I see. Okay, so this length and this length. Okay, so it's your total length, your total effective length of the different wall piers, of the different piers, over the length of that wall line. That's your L effective total. So in essence, it's the sum of the lengths of the 4 dimensions that we would have here in magenta. All right, and that gets then multiplied by this last factor here, L pier, which is now we're back to just our pier. So that would be this dimension here that's in magenta, right? The length of the pier that's actually under consideration. So that's how we determine the force that's on the wall. If you have any questions on that, suggest you just kind of relook at this. And if you still aren't clear on anything, by all means, let us know. Now it becomes simply plugging in numbers. So W earthquake is 5 pounds per square foot. That distance between the walls, between the wall lines, is 40 feet. I think we should probably check these off. The gross length of that wall line was 40 feet. So remember, that's what this line here, from here all the way over to here, right? That's the L wall gross. That's 40 feet. The overhang is a total of 4 feet, meaning there's 2 feet over here, 2 feet over here of roof that overhang beyond that wall. So really what we're doing here, L wall gross over, L wall gross plus over the overhang is really this entire dimension, right? It's the entire dimension of the roof is what we're getting. So the tributary area to this wall line becomes this distance between walls, half the distance between the walls, multiplied by the entire distance of the roof. Okay, so that becomes your tributary area for this wall line. And then what we're doing is trying to get how much of that total force goes into our pier. So again, the overhang is 4 feet, total of 4 feet. The L effective total, meaning the wall piers, the individual wall piers. So obviously this is going to be a number that's either going to be equal to or, this is a number that would be equal to or less than your L wall gross, right? L effective total is going to be equal to or less than L wall gross, depending on whether there's openings in that wall. Any openings, any windows, any doors would subtract from your L wall gross. Or remember, like we had in this case here, where there was a very short pier, so we were just ignoring that. I don't know if ignoring is the right word. Maybe the right word would be it doesn't meet the aspect ratios set out. And it depends on what governing code you have in the region that you operate. But that's why that one got neglected. L pier is 4 feet. That goes back to, let me use another color here. So that goes back to the length of the pier that's under consideration. Okay, let me clear the screen here and scroll down. And so if we plug in those numbers, what we're going to end up with is 880 pounds. All right, so that's the earthquake force on that wall pier. And here's the plugging in 880 pounds. Okay, so now that we've determined that the force on the pier is 880 pounds, let's see how we're going to go about taking that and getting to an overturning moment. All right, so now let's calculate the gross overturning moment. So we know that we've got 880 pounds. How do we want to do this? Well, let's just say so that we can maintain some didn't want to do that. So that we can maintain some consistency in how we've been looking at this. I'm going to, sorry. Let's see if I can do this again without my mouse. I guess my mouse just wants to skip. Okay. Okay, so my mouse is skipping. Really don't want to redo this. So let me just keep plugging away. All right, so in our case, right, remember this was, now we're looking at our wall pier in elevation. And it was at the end, right? So there's really nothing beyond this right edge. I can scroll back up if you want real quick. So what we're doing is an elevation of, where is that plan view? Of this guy here, right? We're doing an elevation of this pier, literally looking from inside the residence, right? We're calculating the uplift on this edge. We're calculating the uplift along this edge with the force pushing the wall pier from left to right. And this was the exterior edge. This was the end of the wall pier. Okay, that's what we're now trying to calculate. So with that, let me see what I need to erase here. Oh, you know what? I'm just going to clear the screen. Well, maybe not. Let me erase, I guess, sorry. Let me erase this, all of this, all of, oh, I should have kept that, huh? So really all I'm saving is the rectangle. That wasn't worth it. All right, let's see. So back to calculating the gross overturning moment. All right. You know what? I'm going to take one more stab at this. So let me just clear the screen. You know, in case I was jinxed with blue, let me do magenta. How about a rectangle in magenta? Can I do that? Hey, magenta worked out better. So there's our wall pier. All right. And uh, and since magenta seems to be working, I'm going to stay in magenta to illustrate the force. So here's our force, right? That's the 880 pounds that we calculated. So now, how do we get the gross overturning moment? Well, we're going to multiply that force times the height of the pier, right? Does that make sense? So let me use black. So we are now multiplying. Let me try that one again. I think I can do better than that. At my age, who knows, but we can give it a try. Let me erase this and this, and let me try again to draw a line here. So, man, no, we're not too good. All right. So right here, right? That's the height of the wall. That's how we would calculate the gross overturning moment. So that's our force, which I think, yeah, we call it V earthquake of 880 pounds times this height of the pier, which is this 8 feet, all right? And that gives us the gross overturning moment. So if we plug in numbers there, we get 7,040 foot-pounds of gross overturning moment. Now remember, what we've just calculated is the gross overturning moment, a theoretical gross overturning moment, right? However, what we want to know, obviously for real world situations, is what is the design gross overturning moment, not the theoretical gross overturning moment, but the design gross overturning moment. So for that depends on the region where you're at, what factors need to be applied to that gross overturning moment. So in some regions, in a lot of regions of the world, you're going to need to use the International Building Code, right? Let me see. And I believe, yes, these are from the International Building Code. So you need to use factors from the International Building Code to adjust the gross overturning moment into a design gross overturning moment. So here are the factors in the International Building Code that apply to, remember, we're using allowable stress design. Let me see which one. Okay, so out of all of these load combinations, the one that is going to govern, in our case, for to determine uplift on the end of a wall, is going to be this last one here. So for this combination, you see that we are taking 60% of the dead load, right? Notice the big penalty, if you will, the big reduction on dead load that we need to take to determine the design uplift. In other words, we want to be real conservative here, right? We want to be real conservative. We want to make sure that we're not taking into account dead load to resist the uplift that really isn't there. So we want to be real conservative on that dead load. So what the IBC has us do is take simply 60% of the dead load we believe is there, the dead load that we've been using to design our structural elements. We take 60% of that, and that we combine, use another color here, that we combine with our ASD earthquake force, which is 0.7 E. So therefore, our gross overturning moment, our design gross overturning moment is going to be our theoretical gross overturning moment multiplied by the factor specified in the again the whatever code you're using that governs in your region. In this case, that factor becomes 1 because we've already this remember that W earthquake that we calculated initially at 5 pounds per square foot, our starting point was already an ASD force. So we know we don't need to take this zero point 0.7 into account. That's already been taken into account. So that's why our adjustment factor here is 1 in this particular case. So our design gross overturning moment, our adjusted gross overturning moment, becomes the calculated gross overturning moment times 1. Therefore, our design gross overturning moment for that wall pier is 7,040 foot-pounds. Okay, so that's how we determine that design gross overturning moment. If you have any questions, please leave them at the end of this tutorial, and we'll try to point you in the right direction or try to provide you a response. Again, if you found this helpful, by all means, please subscribe to our channel, and that way you can monitor and receive notifications of additional tutorials in bridging the gap that we post. Okay, real good, guys.